Howdy y'all, I'm Joe Hughes and I'm here to present my session that's titled From VMs to Containers. This is going to be introductory concepts to containers and some basic live deployments. So let's dig in here. For the agenda of what we're going to cover, we're going to do some basic comparisons and terminology here, right? And we're going to do some comparisons from Windows to Linux, and then from vSphere to containers, right? So hopefully everybody will have at least a basic background in, some of the Windows and Linux concepts. If you're not super strong on Linux, which I'm not myself, hopefully some of the comparisons to Windows will make it a little bit easier to kind of grasp some of these concepts. And then again, doing comparisons between vSphere to containers, hopefully will make a lot of this more relevant to the vMod community itself. Then we're going to dig into some of the resource concepts and visuals. We're going to do some sample container deployments and demos, really super simple basic stuff, just so everybody can see it run and can have some really simple code they can essentially just copy and paste. Takeaways from this, again, basic concepts, quick demos, and then the other resource links is what I expect everybody to get out of this thing. And you also get the chance to hang out with me, so you're welcome. All right, so containers. Again, talking of this as a reference back to shipping containers, right? These are intended to be standardized units that are capable of being shipped and transported easily, right? In this instance, when we're talking containers, we're going to be talking Docker. There are a lot of other container runtimes that do exist. I push people towards Docker just because it's been around, it's stable, it's very well documented. There are lots of easy to consume examples that people can find. So it's really easy for beginners to get started using Docker. So let's kind of go back to some basics, right? Let's break these down. What is it we're talking about when we're talking about a VM, right? So when we look at VMs, and I'm talking just VMware here specifically, right? We start with infrastructure, right? This is going to be your host. This is physical hardware, right? This is going to be your server that's got CPU and memory, it's going to have network, it's going to have storage, all that here, right? So this infrastructure host is going to have a hypervisor installed on top of it, right? This hypervisor is going to emulate physical hardware, right? That CPU, that RAM, that storage and network access to allow every virtual machine, right, these guests, to run inside its own logical run space, right? And then this VM has access to these virtualized versions of the underlying hardware, right? So that each virtual machine, right, the guest, can have its own guest operating system. Then on top of this operating system, right, to make this thing actually functional for us, because an OS is great, but we want it to actually do something, right? We're going to go ahead and install, binaries and libraries, and then like a running application on top of this thing, right? So the entirety of this entity for this virtual machine, it's going to be the guest operating system that was fully installed, the binaries, the library, the application, anything that you have running inside of this VM, right? This is all one gigantic logical construct. It's managed via a configuration file, right? In our instance, it's going to be a VMX file. And that defines the virtual machine for resources and configuration, right? When we need to add another VM, we create another shell for this essentially, right? We install a guest operating system, we add the binaries and the libraries and the applications, right? And this is where we've been for quite a few years now, right? And for some comparison of like what this means when it's Windows space, building a new VM was the outcome that we had when we came to, I've got to run these two applications, and one requires this version of this DLL. The second one requires a different version of the same DLL, right? We're stuck in DLL hell. That's when Windows has no solution for us other than essentially, I need a new version of Windows, right? We go install another VM. Even if we've automated our deployments of VMs, right, this may be where we allow for a golden image, right? So it's another fully patched and updated operating system, which we can then slap binaries and libraries and applications on top of. But the VM is this whole construct, right? We've got to use this this model to deploy virtual machines and manage these things on the scale of multiple gigabytes per virtual machine, right? That's going to contain this configuration file, like our NVRAM setting file, a virtual disk, a log file, all of our traditional VM files, right? When we dig into what is a container, right? Container is going to be a little bit different. So in a container, we're going to start with the same infrastructure, right? We're going to have a host, but this time we're going to be running a container-aware OS, which will then on top of it run a Docker daemon and client, right? So container engine, in this instance, again, we're talking about Docker. So the Docker engine is going to be the Docker daemon and the Docker client. And these will essentially share the host operating system kernel with the containers that are running on top of it, right? The host OS can restrict the ability of these containers to see specific resources of the host OS through namespaces and limit what a container can do through C groups or control groups, right? So these containers themselves will contain like the binaries, the libraries, and the apps, and then whatever commands that we've got defined within this container image, right? So these have no full and complete operating system as part of the image, right? These get managed by a container specification, right? This is a definition file similar to our VMX file, say, for a VM, which instructs the container how it's built and run, right? And that means we actually define inside of this definition file essentially like what base container or what base image we're building from. So we just define the operating system that we're using for this, right? Or the runtime environment that this is going to be. We don't actually have to install, you know, Ubuntu on this thing. We can just tell it start from Ubuntu 1804. So we'll dig into that a little bit further. But as we deploy new containers, because we have a new application, all we have to do is bundle in the binaries and libraries and the application itself that we're trying to deploy, right? So we just stamp these out, okay? So again, with these containers being just the binaries and the applications that are installed that we're trying to actually get into production, this allows for quicker deployment, right? Quick launch, quick testing, even quick deletion of particular apps, right? So a lot of this is going to be really where we're trying to get the biggest benefit out of containers, which is, you know, more application development and deployment, right? So we'll dig into that in just a second. So what's kind of cool about containers, right, is in the end, when it's not running, a container is a file or a set of files, right? It's basically just kind of like a big blob. These files make up this image, right? And this image contains within it the required files and the metadata for the container, right? Once you instruct this container engine to run the container, it unpacks those files and metadata, and then they just get handed over to the guest OS kernel. The resources that a container can see, remember, are limited by the namespaces, and then control of what it can do is limited by the control groups, right? So that's already kind of a known limitation that's there. And I have fun, especially with some of the Linux folks or with more of the DevOps and containers guys. You know, I poke fun a lot with the containers don't believe the hype line. Because once a container is running, right, that's really just a process that lives on this Linux host. That's all it is, right? So I just kind of tell people, you know, yeah, don't believe the hype. Containers don't even exist, right? Because it's kind of funny, but the way you can describe it is, you know, a non-running container is essentially just the image, right? And then a running container is just a Linux process running version of what was defined inside of that config file, right? There's not a ton to this thing. In the end, whether you're looking at VMs or containers, this is really going to come down to your focus, right? Virtual machines provide each VM its own custom OS, right? You don't have to have the same exact definition. You can customize, you can patch, you can configure however you want, even across the same versions of Windows or Linux and such. Whereas containers mean that these applications have a shared operating system, right? And they focus more on the individual app and its dependencies. So this also means that you need to understand some of these fundamental differences and like be prepared for these changes as it's going to relate to your tooling, your automation, your focus on resources and where they're running, how you monitor these things, and even security, right? Because you know a VM essentially is its own self-contained logical unit, whereas a container is now sharing an operating system across all the containers you have running on a host. So just some different things to think about, right? Now, compare and contrast here. VM themselves is going to have hardware version for the virtual machine and hardware dependencies, right? So it's harder to ensure compatibility across environments, right? It might be hypervisor or version or physical hardware and underlying hardware in your cluster environment, all those environmental differences, right? But it's much easier for virtual machines to be oversized for the workload requirements, right? Even though these VMs may only be used during certain periods of time and sit idle for a large percentage of time. Anybody that does any performance monitoring in a virtual environment is probably going to see this pretty much across the board. Right. When we move into the container model, a lot of what we're trying to do here is move from building monolithic applications, and what I'm talking is about the old legacy 3-tier app, where you may have one system that's deployed as a web tier, an app tier, and a database tier. Consider that all one application. If that's all installed on a single system, or if that's deployed as like a single virtual appliance from a vendor, that means every time this thing is built and every time it's upgraded, all of those components have to be tested to work together as all part of that cycle to deploy a new version of that whole bundled application, right? So those monolithic apps are pretty hard. A lot of new application development is switching into the distributed or microservices model. And then we layer in container orchestration, we get benefits of auto scaling, we get all kinds of new stuff with this. But really the thing here, what it comes down to is the fact that, if this container 1 is your web app and this container 2 is your mid-tier application server, right? You can rip and replace each one of these components one at a time. As long as they work and all of your testing is fine, then you can upgrade pieces of your application, of your overall architecture, by like one little module at a time, right? So that's one of the biggest benefits we're going to have here, and as well as the fact that these come down and are measured in megabytes rather than gigabytes for VMs, right? And these workloads really truly can, in these containerized environments, go from a developer's laptop where they've been testing to a dev environment to a QA environment to a prod environment, and for the most part have very minimal issues with anything that's here because the container has everything that it needs within. Okay, so let's dig in a little bit to some more benefits of containers, right? At the container level, it's pretty easy for us to isolate processes. So instead of trying to get better utilization on a virtual machine by installing multiple applications because you're just trying to leverage that base operating system as much as possible, you can build containers that are just very focused for the app or the very component and module that they're trying to serve a function for. And these can still be running on the same host, but have isolation between the processes. That's much easier to attain with containers than it is with a virtual machine. Same thing with file system, right? You can isolate the file system from one container to the next so that they can't see the same files, or you can set it up that groups of containers can see the same resources there. We also have the ability of putting in resource limits the same way that we do with virtual machines. Containers are very, very lightweight. You'll see this based on the size of some of the images we use in the demos, as well as like how quickly these things spin up and spin down, just for how quickly these can become available to us and even responding on the network. And they're portable, right? It goes back to that same container logic of it's a standardized unit we can just kind of move and shuffle around. It's an easy to use format, and based on all the bits that exist inside of these container runtimes, they already have this idea of a central repository. So think of having a content library for VMware for all of your templates to be able to pull from. That logic's built into the container runtimes, right? They use a centralized repository where people like Canonical can put the images for Ubuntu to be openly available that you can just grab off the internet, or you can build your own local repositories to have private restricted access to these images that you're trying to run. So how do these work, right? Again, this comes back to the namespaces. I've listed, all the namespaces out here, but primarily anybody, especially when they're first getting into containers, is really only going to focus on the mount, the process ID, and the network namespace, right? Mount's going to be your storage. Process ID is going to be your actual processes, and especially like what's running on the host versus what's in the container, and then network, right? Because you're going to want to pass stuff in and out of these things. And again, constraints based on the host operating system, you're going to have namespaces that can control what the process or this container can see, and then this control group, which is going to control what a process can do, right? Honestly, some of these can be like in-depth explanations and stuff that I'm honestly not that strong of a Linux admin to get into the very deep dive of what's going on with a lot of this stuff. So you're going to be better off reading into what namespaces and C groups are, both with relation to just running within Linux, and as well as like what benefits they bring and what controls they bring to containers. So if you need some more details about that, honestly, that's a great topic to go look up. There's a pretty good set of information on this stuff as well on the VMware site, the Kubernetes Academy, so kube.academy. So now let's go ahead and jump over into a quick demo for a basic container and some deployment.
All right, everyone, so here we are for our first quick demo on running some containers. And the first thing I want to do is just take a look at our environment and make sure that everything is functional for Docker. So you can see we're running the Docker engine. This is showing that it's version 19.03.8. This was just installed this afternoon on a new Ubuntu VM spun up just to be a clean host for this lab environment. So the easiest thing we can do to just do a simple run of a Docker container to show just a quick test of this is to run the Hello World container. We don't see this image locally. This is the first thing Docker does, is it's checking to see if the image is here in our local repository. It doesn't exist, so it says it's pulling this from the Docker repository here. We do the pull of this image layer. It gives us back all the information about the hash for it and status. And all this container does is spin up, run this command to give us this text output, and then shut down. So if we look at the Docker processes, we'll see there's nothing running in Docker right now, but if we run docker ps-a, this will show us the previous command runs for all. So this shows that this was created and then exited. Basically, it spun up 37 seconds ago and exited 36 seconds ago. So along the lines of the things we were speaking about before, about containers being really quick to spin up and spin down, this shows you, I mean, all it's doing is putting text on the command line, but pretty quick to spin up and spin down compared to a VM. So the next thing we're going to do here is run another Docker container, but we're going to do this one interactively. So what we can see here is we're going to do a Docker run. This DIT is telling us we're going to run this detached interactive and TTY. We're giving our container a name of new_container. We're running it from the Alpine image, and what we're going to do with this is run the ash shell to give us some interactivity. So same thing, we're going to go pull this image. It's a small baseline image for this. And now we're going to run docker ps to say what's going on. Docker shows us we do have a process. It's the container running the Alpine image. It's got our name of new_container that we gave it, and it started 6 seconds ago. That's just running the ash command. So now what we want to do is we will go ahead and connect into this container. So we're giving our Docker exec, we're going to go interactive to the container, new_container, and we're telling it we want to do ping, right? Just ping Google with a count of 4 packets. And we're getting a response back from Google. So this shows us we do have network connectivity. This shows us that the ping command is being sent to standard out, which means we're getting it back here in our console when we're running that command. So that response of the ping is getting sent outside of the container back to us, right? So this is something you definitely want to have for applications that need to actually pass details back and forth from one system to another. So now let's do a quick view of just the Docker network, right? Just to see what's going on here. So we can see that we have a bridge network driver, a host network driver, and a null for no network connectivity driver here, right? Just basics of what comes in by default on just a clean container host that's here. If we want to dig a little bit deeper to see what's actually going on with this container, we can do docker inspect new container, and this will give us back lots of information here. Way more information than we're probably needing at this point. But essentially this will show us, here's the path of what's going on with this thing. Here's the status on it. It'll show you if it's running, if it's paused, if it was completed, what time that was, or like the start time on this container. Shows us what's the platform on it, and then details about the profiles that were applied to this. So really all we want to do at this point is just get back this IP address, right? So we're doing this 172.17.0.2. So what we want to do now is ping that IP. So we can see that ping response from our container host to the container itself is working. Right, so now we're going to run docker stop, if I can spell, new_container. Okay. So we're waiting for this container to stop. All right, our container has stopped. So now we're going to go back and look at the Docker processes again. And we see again no information coming back about a container because there's nothing running right now. But if we go back and look at the history of all, we see our original hello world that we ran, and then we see our Alpine image, which exited 26 seconds ago once we gave it that stop command. So now we can start it back up again. New underscore container. New container is running. And if we look at Docker PS again, we'll see our container is running, has been up for 7 seconds. Now let's do something new. We're going to go ahead and run an Nginx container, right? So we don't have this here. We're instantiating this with the name of new underscore web underscore server. And we're basically saying we want to redirect port 8080 on our Docker host to port 80 within the container. So let's go ahead and inspect this and open it up in a browser. All right, with our browser open, we're going to go ahead and browse to the IP address of the container host and go to port 8080 to see that we have Nginx up and running on this container host, and this port from the container is exposed to the network.
All right, so next let's go ahead and dig into container networking a little bit, right? So all of your container networks are just going to be networks that are all defined based on a type of driver, right? So the network type is going to be defined by what the driver is behind it. And really you're going to base all of these on your needs for handling container to container and container to host communications, right? So the types of networks we're going to have here, right? Host network is essentially going to be the network type that will allow your container to run its network stack side by side to the host networking stack. This also means that you will expose ports from the container on the host itself with no translation. This also means that if you're running multiple containers, say if you're trying to do a cluster of web servers or something, you're only going to be able to expose whatever your shared web service port is from one container, not multiples, right? So it's going to be a downside of using host networking. Honestly, for a decent example that people may have inside of their environments with regards to home lab or running like just home services and stuff, Plex, if anybody's running Plex and you're running it inside of a container, Plex works better when you run it in a host network, right? So it wants that web port of, I want to say 32443 is the web port. It wants that mapped directly from the container to the host operating system that's running it. Just something that people may actually have in their environment, and that might be something that's worth people going to look dig into a little bit more. A bridge network, right? This is going to be the default that will be used for new Docker containers when you add them to your environment. A bridge network allows containers that are running on the same host to communicate with each other, but their IP addresses are not accessible from outside of the host. A custom bridge network, which we'll go through and we'll even create one inside of our demo, is where you can define new rules, right? If you want to tune this network a little bit more for your production environment. This is where you can include allowing a specific DNS, right? You've got the ability to add and remove containers while they're running. You've got the ability to share environment variables between containers, right? You're going to want to do that on a custom bridge, not the default bridge, because you don't want that to automatically be exposed to every new container in your environment if it doesn't have a network specifically defined for it. And then container defined, right? This is a good resource to know about, at least. This is, containers can share addresses and network with another container, right? But there can still be isolation between the containers, but those containers can still allow communications from one to the other on localhost on 127.0.0.1. So if you have a requirement where you need to share address and network between two different containers, maybe sometimes you're trying to troubleshoot and you need access to get to another container with a different tool that you have in some test suite of a container, you might use container defined networking for that. We have good old none or null as defined, right? This is where you have no network connectivity, right? There's no IP and no exposed ports of these containers. I've seen a couple of instances of these where somebody has a purpose-built application or some code that will essentially just go do, say, digging for like security vulnerabilities inside of other containers or other code. Or they'll even do sometimes like code reviews where all they want to do is churn through all the code as it exists inside of a container and generate a report on that. And they can do this without that needing to be connected to the network for any reason, because it's just getting access to the underlying resources on those hosts. It runs what it needs to and then shuts down. There are also advanced networks, and once you get into like multi-host communication, or especially when you start doing like multiple sites and everything, you're going to start looking into underlay and overlay networks. Primarily, like underlay is going to be where you've got MAC VLAN, IP VLAN, direct routing, FAN, P2P, stuff like that. This is, think about applications that need to be working with the underlying physical network directly. So they need to have an IP address and a physical MAC address. So say like a network traffic monitor, that's going to require a physical network address. And then for an overlay network, this is going to be for containers that are running across different hosts, right? In this type of network, hosts can automatically find each other and they can communicate by tunneling network subnets from one host to the next, right? Just using that overlay. This is also going to be where things like NSX are going to come into play. Okay, let's go ahead and jump into a quick demo on container networking.
We're back for demo number 2, where we're going to dig into the basics of Docker networking. So let's go ahead and take a look at our default bridge network that we have here. So the default for any new Docker container is going to be to attach to the built-in bridge network. As you can see, we're running a subnet of 172.17.0.0/16, and we have 2 containers that exist, which are attached to this network right now currently. We have our Nginx container, which was this new _web_ server, and we have our original Alpine container, which we used for just access to a shell. So next, we're going to go ahead and create a custom network, which is going to use the bridge driver. Okay, so we've created a new network named test_network, and we'll take a look at this to see what we have now. So you can see originally we had a bridge, host, and none network, and we now have test_network, right? So we'll get the names of the networks along with the drivers that they're actually using and what scope they are with a Docker network ls. So now we're going to inspect our test network a little bit more. And you'll see where up here we had a 172.17/16 subnet for our new network that we created, this test_network. We are running a 172.20/16 subnet. So new subnet was created for this new network. Now we're going to play around with this a little bit. We're going to repull our Alpine image to 2 new Docker containers. We're going to call them pingtest1 and pingtest2. So now we will go back and do an inspect on our test network again, and we'll see that under containers, we now have 2 containers, right? pingtest1 and pingtest2, which are running and attached to this custom bridge network that we created. So we will go ahead next and run docker container attach pingtest1, which gives us interactive access to the pingtest1 Alpine container. So now let's run some simple tests. Let's run 4 pings to test ping 2. Okay, and we'll continue on with pinging the correct address as we now do ping test 2, not test ping 2. Alright, so now we're getting proper responses back from the container now that we're pinging it with the correct container name, and we're going to connect via IP address now as well. So we're going to send the same 4 pings to IP address and see that we've got this, okay? So now let's scroll up a little bit and pull the IP address that we had from our Nginx container, which we already validated had network connectivity from external to the container. And let's try pinging our Nginx IP address. And as you see, we have ping failures, right? We're not getting from our custom bridge network back to the default bridge network that existed within this Docker host. So we have connectivity via name resolution when we ping with the correct name, and via IP address from container to container on our custom test underscore network, where these are on the same bridge network. But when we go from our custom bridge network back to the default bridge network to try and go from our ping test 1 VM back to our Nginx VM, we are not crossing the boundaries of those network drivers, those defined networks that we have.
All right, so the next topic that we're going to dig into is container storage, right? This is not what I'm talking about, although this paints a decent picture when it comes to container storage. If you're not defining storage for your container, it is ephemeral, right? This means that if you're not actually using some of these persistent storage methods that we'll talk about in a minute, then the I/O of your container exists while it's running and while it's on the network. And even if you shut down the container, all the data will be stored within this container. But then when you go call pods and say, I'm done with this container, and they come pick it up and take it away, or you delete this off disk, that's it, it's gone. It's as if this never existed. It's essentially the same thing as, only having data that ever existed within a virtual machine, and then you go delete that virtual machine. When someone comes to ask for that a month later, it's as if it never existed. So that's covering non-persistent storage for containers, right? And now we have a couple of different types of persistent storage to go through here. So the first thing is going to be volumes, right? Volumes are created and managed by Docker, right? They naturally go under a specific file path inside of your Docker environment. A volume name is enough to mount it, right? You don't actually have to give it a full path for these things, and it's pretty quick and easy to back up and recover these things, right? And you can create them, pretty interactively, whether you're doing CLI or API. It's pretty clear advantage. One of the other methods we have here is bind mounts, right? These are not managed by Docker, right? These can be any location in the host machine, but you must provide the path to the host machine to be able to mount it, right? So it's a little bit outside of the context of Docker that you have to describe these things. Backup and recovery of data on bind mounts is a bit complicated, but it's not difficult if you know what folders you need to back up, right? Bind mounts also cannot be accessed directly via CLI commands, right? You can still work with them on the host machine directly, but not through just native CLI, right? The Docker volume can be created while creating the container, right? And it can be used with data that's created and used by the container itself, whereas a bind mount only gets created when the folder doesn't exist on the host machine, and it can be used to access data from the host machine itself, right? In the end, bind mounts are really recommended if you're using large amounts of data, right? Huge data you want to be in a bind mount, not in a Docker volume. The other type of storage that's also available to you is going to be Temp Fs. This essentially gives you a writable location. Think about this being like a write to memory, or something similar to, say, like a /dev null. This is a writable location that specifically does not persist when you have shut down or destroyed the container, but it's written to a place that this does not end up impacting the the host operating system file system operations, right? Think of it kind of a scratch space type of thing. And now we're going to jump into a quick demo on creating a container image.
Welcome back for our final demo here. We're going to run through creating a Docker image just interactively here at the command line. So rather than Alpine, this time we're going to pull down a little bit larger of an image. We're going to go for the Ubuntu 1804, and we're going to go ahead and run this interactively, which means we're going to drop down in. You will see that as opposed to the jhughes user that I had on the Ubuntu host, we are now running as root within this container. So we're going to do something pretty simple here. We're just going to echo out hello world to /message and then exit out of our container. So now that we're back at the host prompt, let's do a docker ps to see what we have running. And we have no containers running currently. So if we do -a, we'll see that we have the Ubuntu image here that exited last 10 seconds ago, right? So all we're going to do now is essentially do a commit on this. So we're going to do a docker commit. We're going to grab the name of this, and we're going to give it our own title for the image itself. So based on that container that was running, we're creating an image from it. We get back a hash. So now if we do a docker image ls, we will see that we have the Ubuntu 1804 image that we pulled down, created 4 days ago, and we now have the hello_world_local image, which defaults to a tag of latest if you don't give it one, that was created 9 seconds ago, and it's the same size as the source of the Ubuntu image, right? Because all the layers on this are essentially going to match. So now we're going to do really quickly, we're just going to run this hello_world_local and cat out the /message, right? So it still has that hello world text that we had it echo out when it ran under the original container instance that was based off of the Ubuntu image. So now that we have that, we are going to say we like this change, we want to go ahead and commit this, right? So what we're going to do here is run this change, which will say for this command, what we want to do is cat /message, right? And then we're going to pull that process information back, and we're going to retag this as hello_world_local tag name fixed, right? So now if we do a docker image ls again, docker image ls, if Joe can type, you'll see that we had the latest tag about a minute ago, and we now have a new tag of fixed, which was created 28 seconds ago. Again, about the same source size as the original Ubuntu image. But now, if we run a instance of the image with this fixed, what will happen is it will automatically return to us the details of the text that were within /message, because we added the command to Docker to say, once you're up and running, once you've instantiated, you've unpacked the files and the metadata, what we want you to do is actually run this command, right? And we get back that output from the standard output. So we've now essentially cloned an original image to something that we wanted, right? Injected a tiny little bit of source data into it, and then retagged it and said, as part of this container for our custom version, what we want to do is actually run this single command line. And we now have this done.
All right, now we're back from the demo. You guys have seen the quick basics of creating a container image at the command line. All right, so wrapping up. Now it's lab time for everybody else. I challenge you guys to go pick up some basics, go learn a little bit about containers, go play with this stuff. And in the end, honestly, if you get a container up and running in your environment in a lab, and if any of that came in any way from this presentation, I will declare us all winners from this. Thank you all. The additional resources you guys will find here, I've set up a bit.ly link for it. You can find me on Twitter at jhughes. I'm very easy to find with the green hat, obviously. Thank you, everybody, for joining. Please volunteer to speak at a VMUG event if you have anything you would like to present on. We're even trying to put together some slots to do 5 and 10 minute long quick presentations for remote presenters to the Austin VMware user group. I would be glad to have anybody reach out to me and say that they want to present on a topic. And join the V community, right? Jump online and just search for the V community hashtag. You will find tons of us geeks talking about all kinds of things, from movies, Star Wars, food, pizza wars, all kinds of things. If you're not in the conversation, get involved. Reach out to me on Twitter if you want. If you want to drink from the fire hose, reach out to Ariel Sanchez Mora. I would love to see everybody here pick up, learn some things, do a presentation back, and just contribute back to all of us. And thanks to VMUG for putting on the event and giving us all a chance to hang out together. All right, thank you all. Everybody stay safe. Have a good one.